radiations which are coming from, for example, from the sun, from the bulb. So these radiation, they interact with. This is known as absorption spectra. And when it is emitting the radiation, it is the emission. The pattern of the absorption as well as the emission, that is known as spectra. Okay. It is not a single method, it is a set of methods, that is where interaction of the electromagnetic with chemical molecules, it could be atoms, it could be molecules, it could be ions. So these chemical but with the molecules, and that is measured, that's the radiation which is being measured. It is being measured how much it is being absorbed, which type of radiation are being absorbed by a molecule, and to obtain the characteristics. So this absorption of the electromagnetic radiation by the chemicals molecules, they are a specific one. They are not routinely. All the molecules are not absorbing. All the radiations are not being absorbing. All the radiation are not being evolved. So the specific amount of specific radiation which are being absorbed, and they have a characteristic pattern. Predict certain properties. We can predict the quantity of a material, for example. Spectrum. Okay. Now the atoms and molecules, they interact. They could may absorb or they can emit the electromagnetic radiation in a wide variety of ways. There are so many ways in which the atoms and the molecules, they can absorb or they can emit the electromagnetic. That is not a single one. There are so many patterns. We are going to discuss within a couple of slides. They stimulate different types of motions, different types of interactions. जी अस्सलाम सकते हैं, मुझे ये बताएं। यहाँ तो सब कुछ मेरे पास तो सिग्नल सारे क्लियर हैं। डिस्टॉर्शन होना और चीज़ है, आवाज़ ना आना और चीज़ है, एक चीज़। दूसरी बात है कि यहाँ हेलो तमाम स्टूडेंट जो हैं वो अपने अपने सिस्टम को रीस्टार्ट करें, probably it will be working. At my end, it is everything is okay. So please try it. Thank you. Okay. Now, this absorption of the electromagnetic radiation, they are depending upon the type of the motions, type of the interaction in the atoms as well as in the molecules. Okay. Now, and when they are absorbing a different types of the radiation, they have different types of the motions within the molecules and the atoms. So the pattern they will be different. That is the pattern of absorption. That is which is being absorbed, and that is absorbed to what extent? It is absolutely absorbed. It is partially absorbed, or it is if it is emission, which type of the radiation are we are emitting, and which time, how intensity of these emission lines are. Now, this pattern of absorption or emission is known as spectra. Spectra is the plural form. And spectroscopy is what? Spectroscopy is the science which is dealing with the study of the study of the spectra, interpretation of the spectra. So the spectra is concerned with the interpretation of the spectra in terms of what? In terms of atomic or molecular structure. So at atomic level and the molecular level, interpretation of the spectra, which is the trace of the absorption of different radiation, is known as spectroscopy. So we are dealing with this spectroscopy in this class. Now, if you see, when we say electromagnetic radiation, yes, electromagnetic radiation have a different regions that can be used for qualitative as well as quantitative information. And this qualitative, there are different types of the chemical informations. Now, for example, this is the whole spectrum. That is the which is coming from what? From the sun. Now, this is, for example, the gamma rays, X-rays, UV, then visible, then IR, microwave, and then radio waves. So these are different regions of electromagnetic radiation. So this is the gamma rays, which are highly energetic, just like X-rays, high energy ionizing radiations. Then coming to UV, high energy radiation, followed by the visible region, whereas salmon color waves go, that is the then the infrared, that is we are feeling the heat. Then there is the microwave, that is again molecular levels, like, and then radio waves, they are the very long radiations. They have very long wavelengths. High energetic, but they have low wavelength. Whereas the radio wave, they are very weak, but they have very high. This is the wavelength. It is decreasing few waves to gamma rays. So minimum is the gamma rays. We are going to see slide. This is the whole spectrum. And we are studying at this moment only not gamma rays, not IR, not microwave, not radio wave. We are only UV visible. That is of our interest for two. This is again. This is what? This is again the X-rays, gamma rays, then the UV region, that UV, and then there is a very small portion that is the VIBGYOR, visible region, that is ranging from violet, blue, green, yellow, orange, and ultimately red. So 7 colors. Beneficial for the human beings. Okay, then there is microwaves. We are using this microwave in our daily life, and then we are we are listening the music and other on the radio. So these are the radio frequencies. Now, if we see the wavelength for this wavelength of the radio waves, for example, it is ranging from about 3 kilometer. 3 kilometer. Yes, this is very long wavelength of radio, and then it is decreasing. Right? And this is, for example, this is it is 0.03 millimeter, and then there in the visible 300 nanometer ultraviolet. This is 300 nanometer, and this is 3 nanometer, and then coming back, and then this is picometer, that is X-rays and gamma rays. So these are very high energy radiation. They have the wavelength is lambda is very low, but they are very high energy. Now, in the definition, we studied that there could be the emission. Now, this is what that is. There are two main classes of the spectra, namely the absorption spectrum and the emission spectrum. Now, this is the absorption spectrum. This is a normal, for example, atomic level. This is the first energy level. This is second, third, fourth, fifth. Similarly, now if the electron is here in the ground state, and if we bombard some energy, if we apply some energy to this electron, it will be excited. It will be excited to higher energy. Excited. These are the excited energy level. This is first excited energy level. This is second, third, fourth, and so on and so forth. Now, if by the absorption of energy, this electron is jumping from ground state to excited state. Atom is supplied, so it will be jumping from ground state to first excited state. If greater energy is greater than that, it will be jumping from ground state to first, second energy excited energy state. And if, for example, further high, it will be jumping from this ground state to third excited state. So this is the absorption. Absorb the energy from the source, from a radiation, that is H nu, that is represented. And this is absorption if when it go from low energy level to high energy level. But the reverse phenomenon is also there, that when it is from high energy level to low energy level, it will be emitting energy. It will be emitting radiation, and that is what that is that this energy, emission of energy from coming from high energy level to ground state, it is the exact same as was supplied in the absorption phenomena. This is exactly the same. Here energy was supplied. Here it was energy being removed from the system, that is atom, for example. And this is the energy scale, that is the energy is increasing. This is ground state, first excited state, second, third, and fourth, and so on and so forth. So we can say that the absorption, there are this is the first absorption spectrum, this is second is the emission spectrum. Definition is that a transition from a low energy level to higher energy level with the transfer of energy from the radiation. From the radiation, it is absorbing from the radiation field to the absorber. Be a liquid, it could be a gaseous form, but it is the absorber. Now, when it is absorption, it is known as absorption spectrum. And the other way is that taking from higher energy level to ground level, it will emit energy. It will go to higher energy level to low energy level. The energy is transferred from the emission, from the emitter to the radiation. It is exactly the source of that is the absorption. And this energy, for example, from jumping from this energy to this energy level, this is known as delta E. This is E2 energy, that is high energy level. This is E1. E is equal to E2 minus E1, that is equal to H nu. H is, that is proportional to what? Proportional to the frequency which is being absorbed or which is being evolved. So which is being absorbed, which is being emitted. So this is H is the proportional. E, that is the energy gap, is directly proportional to what, that is the frequency of the absorption or emission. If, for example, there could be a possibility that there is no radiation, emission of the radiation or absorption of the excited state, in that is called, that is not that is not depending upon the radiation. That is just a smaller, lower energy level. Now, again, the same one. There are two categories, that is the absorption and that is the emission. Yes, energy delta E is equal to H nu. That is exactly the same. So this is the absorption. We are supplying energy. Here the emission is an emission from the atom from this any absorbing species. It is, that is the, this is the emission. And again, equation delta E is equal to E2. E2 is the energy of high energy level, where this is the low energy level, that is equal to H nu, where H is the proportionality constant. Now, जी इकरा, क्या प्रॉब्लम? Is there any question? इकरा रहमान. Hello. रोहेल एरिक, मंसूर अकबर, इकरा रहमान. मेरे एंड पे एवरीथिंग इज ओके. आप अपने सिस्टम को चेक करें. यहाँ पे सब कुछ एवरीथिंग इज ओके. सिग्नल आ रहा है, सिग्नल जा रहा है. Please, thank you. So when we say that this is the absorption as well as the emission, so now we are dealing with what? Electronic spectroscopy, infrared spectroscopy, microwave spectroscopy, nuclear magnetic resonance, and then electron spin resonance. All these are what? These are the category. They are the absorption. They are working on the absorption mode. Whereas on the in the emission mode, we are dealing with what? With the, we are studying the fluorescence, and as well as we are dealing with the phosphorescence. So this will be, we are dealing with some other time, but now today we're going to study the electronic absorption spectroscopy. Now, there are certain basic things you must know in the UV visible spectroscopy. And now we up till now we know that the spectroscopy is the study of interaction of matter with the electromagnetic radiation EMR. Now, the electromagnetic radiation possess the property of both the particle as well as the wave. So they have the both the property they are present in the electromagnetic radiations. The particle component is called as photon. Yes. So this is a because this is a property and the particle property. So the particle property is known as photon. And the energy component of photon proportional to the frequency, and it is related as with the according to this equation that is known relationship. Delta E is equal to h nu, where h is the proportionality constant, and we say that this is the Planck's constant. These are the first scientist. He discovered that this proportionality constant is there. Again, this is E1, this is E2. This is the absorption, that is energy absorbed by means of absorption. It is coming from what? From low energy level to high energy level. Now here h is the Planck's constant and mu is what? That is the frequency in hertz or in cycle per second. This term, that is a photon, means a small massless particle that contain a small wave packet of electromagnetic radiation or a small packet of light. And we are using the terminology within this course, that is the photon or electromagnetic radiation. They are all intermixing. That is, it means the same. When we say photon, it means that it is the energy. Next point is, we know that the speed of light is c, always constant. The frequency is what is the frequency? It is a number of cycles, and this and is inversely this frequency inversely proportional to what the wavelength. So the relationship between the light frequency and the wavelength is like that. That is nu is equal to c over lambda. This is what, this is the delta. This is delta E, change in energy. That is equal to h nu. We have already studied this equation, and then that is equal to hc over lambda. Okay. Now E is equal to mc square. We know that is the Einstein's equation. Okay. Now combining this equation with this, and we can rewrite this equation as mc square, that is equal to hc over lambda. Ultimately, that lambda is equal to h divided by mc, and this is the constant. For example, this is as particle. They have a particle nature, that is, it containing what it is a mass, whereas the wavelength, it is the wave property. Okay. Coming to what? The radiations. The electromagnetic radiation interact with the matter in the two different ways, such as number one is the collision and number two is the coupling. So the collision is the process in which particle to particle collision is taking place. Colliding with the other particle, the energy is lost as heat and movement. When, for example, which is of higher energy, when it collides with another particle of low energy, it transfers its energy from high energy particle to low energy particle. So some heat transfer is taking place. When heat is being transferred to the low particle, its movement will be increasing. Means its kinetic energy will be increasing. So this is the process that is called as the collision. So particle to particle collision taking place and the energy is lost during this, and heat the heat as a heat loss or as a the movement of the particle. It's a particle the first it's which has a high energy will be decreasing, its valency, its movement will be decreasing, whereas the particle which of low absorption of energy, it will be moving faster, its movement will be increasing. So this is particle, because this is the particle collision is there. Now, what about the coupling? Coupling is related with the wave property. Wave property of the radiation matches with the wave property of the particles. Now, every particle, for example, when we say that atom is there, atom is, and it is its movement is what? Its movement is like a wave. So when this wave is exactly equal to or matching with that of the radiation, it will be coupling with each other and it will be exciting. It will energy level means to it will be absorbed, it will be coupled to what? To next higher quantum mechanical energy. Wavelength is the linear distance between the two maxima or two. Yes. So it has two. This is the crust. This is the maximum. This is two conjunctive minima. That is this is the distance, linear distance, starting from one maximum, first maximum to second maximum to third maximum. They will be the same one. Or this is the amplitude. This is the zero. That is the center point. So it is this is positive and this is negative. Positive and negative. Positive and negative. Wave motion. And now where the point which is on the same axis, and that is known as node. This is the nodal point. So again, the distance between the two consecutive nodal points is again the wavelength, that is the lambda. Well, capital A, at the top of there is a circle that is angstrom. So this 1 angstrom is that is equal to 10 raised power minus 10 meter. 10 raised power minus. Okay. So now there is another terminology which is known, and that is the wavelength, that is nanometer, that is nm, nanometer, nm. So 1 nanometer is equal to 10 raised power minus 9 meter. Then there is micron, that is a simple a Greek letter, that is 10 to the power minus 6 meter. Then there is what? Micrometer. 1 micrometer is equal to 10 to the power minus 3 nanometer. These are the units which are being generally used in case of when we are measuring, when we are dealing with what? With the wavelength. Now, the frequency. So frequency is the number of waves per second which are passing through a point in 1 second unit time. So the number of waves per second is known as frequency. It is generated by, and this is, it could also be expressed as cycles per second. It could be named as hertz. Now there is another one. That is the wave number. That is reciprocal of the frequency. That is 1 over lambda. So 1 over lambda is the number of waves in a unit length. For example, 1 centimeter. So the number in 1 centimeter is known as centimeter inverse. That is the wave number. It could be in meter. That is in 1 meter. That is per meter. So it is the reciprocal of the lambda. That is 1 over lambda, and is direct measure of the energy. Now, it is the reciprocal of the lambda, and it is a direct measure. So it means greater the wave number, greater will be the energy. Lesser the wave number, lesser will be the energy. It means that 100 centimeter inverse is lower of energy as compared to 300 centimeter inverse. Now, there is another one, that is the velocity. That is the product of wavelength and the frequency, and it is equal to the velocity of the wave in a medium. It is always measured in centimeters per second, or is equal to lambda into frequency. And when it is light, it is c. It is constant. Now, and this is the relationship between the frequency and the wavelength of the velocity of light in vacuum. That is equal to lambda into frequency constant. It means greater than this is the constant, and it is the relation. It is, if it is greater, if it is lesser, it will be greater, so and so forth. Now, velocity of light, it is in the vacuum, it is fixed 3 into 10 to the power 10 centimeters per second, or it is 3 into 10 to the power 8 meters per second. Okay. Now, coming to the photon, again, it is the energy quantum. So, energy quantum is that the quantum measurement, that is the nature of the light to explain the photoelectric effect. So, this is the photon. This is being related, that which is being confirmed by means of the photoelectric effect. It means that the photon, a fixed quantum of energy. The energy of a photon is proportional to the frequency of the radiation, that E is equal to h nu, or E is equal to h nu, or E is equal to h into c by lambda, because mu is equal to c over lambda. So if we replace c over lambda in this first equation, so we are getting E is equal to h into c by lambda. So this is the relation between the frequency, radiation, and energy. Now, talking about the radiation. So we have already studied in some previous slide that X-rays of high energy level as compared to visible, which is again high energy level as compared to IR and the microwave, and then so microwave and the radio wave, they are of low energy level, but they have high wavelength as compared to what? As compared to X-rays and the gamma rays. So which have high energy, but they have low wavelength. So how? For example, what? That is the emission of electrons from the inner shell are taking place, and we are observing. We say due to this ionization, the X-rays are being generated. So this is the basic phenomena that this energy is sufficient, high energy is required to eject the inner electron of the inner shell is the origin of the X-rays. Similar, but we are not going to detail. I am giving you just an idea how interacting with what with the matter. Now, some lower energy, that is ultraviolet and the visible region, that is being electrons are being excited from low energy level to higher energy level. So it is just the excitation, it is ionization. It is just absorption of energy from low energy level to high energy level. It depends upon lower energy is being supplied. It is jumping from ground level to first excited state, or it is ground level to second excited state. It depends upon the energy quantum. It is the wavelength which is being bombarded, which are being interacting with this atom. Then lower energy, then UV visible, there is IR. IR means that is the molecules are vibrating. They are not exciting, but their excitation is on up to the vibration of the bond. For example, this is carbon, this is oxygen. So this oxygen carbon moving, they are elongating, they are contracting. So this is again known as vibration with to their mean position. So this much is sufficient to excite energy required. Similarly, for this is the vibration, and now here it is the rotation. So this is again quantized, and this is where this required very small energy. So this is that is a microwave radiation. They are being sufficient to excite these levels, that is a molecular rotation. So this is just this is just an idea that greater the energy, greater the energy, it has impact on this molecule or atom. Less of the energy, less is the impact. So this is, but we are restricting today on the two UV visible radiation, that is the electronic transitions. Now, and this electronic transition, that is UV, that is spectroscopy. This is very important technique. It stimulates, radiation stimulates molecules. We have seen in the previous slide, the electrons are being excited from low energy level to high energy level. And this absorption of the spectroscopy in the region of what? In the region of 160 nanometer to, in some books, it should be ranging from 200 to 780. Some other books, it is 800. So it is just a matter of choice, for example. But this is the major range. Now, the measurement could be absorption or transmission. When it is being energy, from low energy to high energy level, it is the absorption. When it is jumping from high energy level to low energy level, it is the transmission, it is the emission. This can be used, this UV visible spectroscopy could be used for the identification of what? Identification of inorganic or as well as organic molecules, organic or inorganic species. And this provide us this UV visible giving us the information regarding the presence or the absence of a functional group, organic compound. There is a functional group, that is hydrocarbon, then alkyl halide, then ketone, carboxylic acid, esters. So all of them, they are present. They are due to their group. They have their own absorption range. So this is being used for the regarding the saturated or unsaturated functional group are present. Double bond, single bond. We can determine which type of the a functional group is present, as whether it is LD, alcohol, whatsoever. So we can also determine the concentration of particular substance, especially in chromatography when we are using the way at the where the output of the chromatography is coupled with that of the UV visible, so it is giving us the absorption signal. Okay, in the gases phase, electronic spectra of the diatomic molecule, that is very, very important information. That is the electronic spectra of the diatomic molecule resolution, that is important, show both the vibration as well as rotational structure, rotational vibration of the molecules, which enables us to determine the bond length of a homonuclear diatomic molecule, such as nitrogen, such as iodine, such as bromine, such as hydrogen. So, such type of molecule, when they are being excited in the electronic, so these are diatomic molecules, due to their high resolution, their vibration of the motion, vibration between the two, their mean position of the, we are able to determine what the bond length of these species, such as nitrogen, hydrogen, argon, not argon, it is the diatomic, iodine, fluorine, bromine, iodine. This technique is very suitable to identify, to measure the bond length, bond distance between the two atoms. They can also be essential. This is the beginning. This is the first step, so that it will leading us to a right pathway, that whether we will check whether a functional group is present, whether single bond is present. So this will give us a proof that this information is bond is there, we will say that this is the alkyne. If nitro group is there, we say that this is nitro group compound. So final for this is essential step for the for further study of the molecule. Now, when we say that this is essential, some photons are being absorbed, so mean that electronic spectra can be characterized by special group of atom or atoms, which are known as chromophores. So this chromophore, this is a specific characteristic atoms or group of atoms we are going to detect within a next a couple of slides what is chromophore. So due to this chromophore, this chromophore is giving us characteristic radiation is being absorbed. For example, alkane, it will be absorbing at different wavelength as compared to alkene, different wavelength. Then as compared to alkyne, it will be absorbing at different wavelength. So although the carbon, but there is carbon-carbon double bond, carbon-carbon single bond, carbon-carbon triple bond. So these are the functionality that the alkane, alkene, alkyne, and they are using characteristic absorption. They possess characteristics. They will be absorbing at different wavelength. So when they are absorbing at different wavelength, we can identify it is unsaturated compound alkene or alkyne. So again, when we say that it is the alkene or alkyne, both are unsaturated, it means there should be some difference. And that difference could be determined by the help of absorption wavelength, which is different for double bond or triple bond. What is the origin? What is the origin? How the electronic spectroscopy is obtained? So we know that these are energy level. Yes, this is energy, this is a low energy, this is a high energy, this is further high, this is further. Again, if we categorize these atomic energy levels, that is, these are the energy level in which these are the energy levels which are in which there is no electrons are there. So we can categorize all these atomic energy levels into two types. One is known as homonuclear, homo at orbital, and the other is known as the LUMO, LUMO. So homo or LUMO. So it means that homo means compound in which these orbitals they are occupying maximum number, and the LUMO is which are not obtaining, they are unoccupied, they are empty. So okay, so it means that when this is these are two, for example, two, although it is a two different energies, this is for example 1s, this is 2s. So 2s is of higher energy as compared to 1s. But this electron cannot be jumped from here to here. So it means that this could only possible that this saturation is going to another element or atomic level which is electron deficient, in which there is a vacancy, open vacancy. It means that this comes from low energy level to this high energy level. So when this happens, we say that the transition is taking. Okay, so it means we can say safely that the UV visible spectrum will be observed when the electron is jumping from homo orbital to LUMO orbital, means low energy level to high energy level. Yes. Okay. Now, in words, that the electronic transition involves the promotion of electron from the electron ground state to higher energy level, and usually from HOMO to LUMO. So, a molecular orbital called as HOMO to LUMO. Okay. Now, the HOMO means, in other words, we can say we are saying that they are occupied. It HOMO stands for. HOMO means highest occupied molecular orbital. Occupied by what? By the electron. The orbitals which are maximum number of electrons, those are known as HOMO. So there, not from when from LUMO to HOMO, it means that will be the emission mark. Orbital. This is LUMO orbital. So this is for example, this is paired electron is there. No other no other electron can be occupying here because it is already paired one. So when we supply energy, delta E, it will be coming, and this energy, if it is exactly matching it, when this energy is exactly matching with the energy quantum, that is pi to pi star, from energy gap between the HOMO to LUMO, the excitation, it will be electron will be jumping from low energy level to high energy level, like this. Of electrons, so it will be jumping, and H nu is being absorbed, so this will be jumping from low energy level to high energy level and forming what, like this, and that is the energy level HOMO, and this is LUMO. So HOMO to LUMO is there. So that is the basic condition, that the energy electron will be jumping from low energy level to high energy level, but the high energy level must be empty. High energy level they should accommodate the saturated saturated shell from low energy to go absorb electrons to at higher level. So that is the promotion or excitation from homo to lomo, the basic requirement. And this is again it is the same one but in a different way. So this is energy. So when this is the molecular orbital theory. So this is the atomic orbital. So atomic orbital when they combine they form molecular orbital. So when atomic orbital combine they form some bonding molecular orbital. The other one that is the anti-bonding molecular orbital. So bonding molecular orbital they are always of lower energy as compared to the orbitals energy of the orbital from which these are being formed. Whereas the anti-bonding molecular orbitals are those orbitals which are of higher energy level as compared to the atomic orbitals from which they are being generated. For example, there is a sigma bond formation there. That is the bonding sigma bonding molecular orbital is there. When sigma bonding molecular orbital, there is always a anti-bonding molecular character here. That is sigma star is there. Opposition. That is opposite one. Now, similarly, if for example pi electrons are there, pi electrons from, when they are combining, that is the pi orbitals, it means they are forming pi star orbitals also. This is the energy level diagram of what? Of a molecule. So this is molecule orbital diagram. So it means the stable is what? That is the sigma bond. So this is the lowest energy level, followed by a double bond. That is the electron. This is also stronger. And then there is in between there is non-bonding and orbital. Sorry, non-bonding are those such as you know that the nitrogen has a one lone pair of electrons, and this electron that is known as non-bonding orbital. Okay, this is bonding orbital star. This is bonding uh, simple. This is star. This is simple without star. Okay. Now, because sigma is the most stable, it is the lowest, followed by the pi electrons, and followed by the non-bonding orbitals, and then there is pi star and the pi sigma star. So this is the energy level diagram of a molecular orbital theory, according to atomic molecular orbital theory. Okay. Now, when we say that the atoms, sorry, the shell which is of lower energy as compared to non-bonding orbital, those are occupied orbitals. So these are, we can say these are the HOMO, these are the LOMO. So the energy always the jumping from HOMO to LOMO. Okay. My electron, the orbital of lowest, highest occupied orbital, highest that is saturated with what? With the electron. To what? To when so it's mean that when we say that, for example, electrons are highest occupied orbital, it is jumping from low energy level to high energy. So this is what? Sigma to sigma star is present in what? Alkane, saturated compound, methane, ethane, propane, nonene, decane, and so on and so forth. So all of them they are the single bond, separated compound single bond. So the electrons are jumping from sigma to sigma star because the bonding that is which is by the equal sharing of carbon and hydrogen, that is covalent bond, that is called as sigma bond. So sigma electrons which are being involved, they are called as sigma electrons. So sigma electron, they are jumping from sigma to sigma from this scale, from this energy scale. This is lowest energy level, this is the highest one. And we know that the sigma bond is the most stable as compared to double bond and the triple bond. Yes. See, that is sigma to pi star. Sigma to pi star, it is of lower energy level as compared to sigma star. See, another one that is sigma pi to pi star. It is again less energy as compared to sigma to pi star, like this. And this is sigma to pi star means it is, for example, carbonides are there. Carbonides are there, they are of low energy as compared to, it's the lower energy means how we can see that when it is absorbing at longer wavelength as compared to alkane, we say that this is of wavelength, this is the energy gap is that's. Then there is another one, pi to pi star, that is alkene, double bond, alkene, ethene, propene, butene, a triple bond. It falls into pi to pi star, that is propine, so and so forth. Okay, pi to pi star, and then there is from non-bonding to upper level, that is sigma star. This is of high energy level, and this is of low energy level. So but we can measure this energy gap between by when we are measuring this when we are using the electronic, this will be alkane will be absorbing a different region in different region as compared to, and carbonide will have a different region as compared to alkene alkyne, and this is we have different region, sulfur, nitrogen, oxygen bonds are there. Okay. Now there is another carbonide pi star, that is non-bonding electron. They are being jumping from non-bonding to high energy level. That is the pi star. That is in the case of carbonide, for example. Carbonide means carbon double bond O, that is aldehyde, or as well as oxalic acids. The same picture is there. That is the sigma, pi, and pi star, and now these are the transition we are taking. This is sigma to sigma star. That is our maximum energy. This is occupied orbital. These are unoccupied orbitals. These are LOMO. So HOMO to LOMO are there present. So these are the occupied orbitals. We can't say that this is LOMO to LOMO. No, maximum. If they are possible, LOMO to LOMO, but they will be very weak intensity, very unstable as compared to what? As compared to this HOMO to LOMO. That is very strong peak will be there. Now there are two different important terminologies. You must know it. One is the chrome and the other is the oxochrome. When we say that alkane is absorbing, carboxylic acid is absorbing, so they have different meanings. That is That is chromophore. Chromophore is a what? Is an atom. It could be an atom or it is a group of atoms. And this covalent bonded, for example, unsaturated compound, alkyne. Similarly, carbon double bond O, carboxylic acid, aldehyde, ketone. So this could be chromophore, could be an atom or a group of atoms. When we say it is an atom, for example, a chloro group, chromo group, fluoro group. So this could be an atom or a group of atoms. For example, nitro group. So it could be chromophore could be an atom or a group of atoms which is covalently bonded to unsaturated groups. Now, this is an atom or group of atoms whose presence, it's due to its presence, the molecule is responsible for the absorption of the radiation. Due to if absorbing in this UV visible region, but due to the presence of these groups or group of atoms, this to absorb radiation in the UV visible region. So such compounds are known as chromophore. And there are two types of the chromophore, especially in the organic compounds. Because compound, that could be inorganic compound. Okay. Now, so there are two. Number one, that the chromophore which contain pi electrons only. It means that there are when it is unsaturated bonds, it means there are carbon-carbon double bond. It could be ethylenic or acetylenic. It could be carbon-carbon double bond. It could be carbon-carbon triple bond. So because in this double bond, the pi electron character is there. Pi bond is there, so pi electrons are there. Here two pair of electrons are there. Again, there is again pi to pi star transition taking place. Now this is the only battery that is only double bond is present. Is that chromophore which contains pi electrons as well as non-bonding electrons. It's triple bond. There is a compound, there is an element, there is an atom which is containing, which is there could be the idea is that nitrogen has a one lone pair of electron, oxygen has a two lone pair of electron, chlorine is there, it is containing, so no. So it means that they do two types of transitions. So because by virtue of the pi unsaturation, pi to pi star is there. Are present in this type of chromophores. The example could be carbonyl, C double bond O. Now there is a double bond, for example, so the pi to pi star transition will be there. But this oxygen atom, it is containing unused pair of electrons, that is non-bonding electron. Is also present. Similarly, as a group, for example, nitrogen, nitro group, NO2 group, nitrate group, NO3 group, nitrite group, NO2 group, So these are few examples on this, that there are two types of chromophore. One is on the containing pi electron, the other contain pi as well as the non-bonding electrons. Now, oxychrome. Oxychrome is absorption band of its own. It don't contribute to the absorption phenomena by its. So when this oxychrome is conjugated, it is being coupled with a chromophore. It it gives rise to changes. It will change the wavelength of this chromophore as well as its intensity. Its absorption will be increasing. So this is the oxychrome don't give rise to its own spectrum, but when it is conjugated with the chromophore, it changes the intensity as well as the absorption wavelength of the chromophore. It changes the chromophore characteristics. It may be an atom or a group of atoms. Yes, it could be a group of atoms. It could be a simple atom. We are going to just having a example of that. Its color is changing. It is color enhancing group. So due to the presence of this group, the color of the chromophore will be increasing always. So it is a color enhancing group, such as methyl group of the oxochrome. So they don't absorb their own, but when they are attached with somebody else, it will be changing the absorption characteristics of what? Absorption characteristics. Okay. Now the attachment of the substituents. Now the attachment of the substituent hydrogen on the basic chromophore structure changes the position as well as the intensity of the absorption band of chromophore. Now, for example, is consider for example a benzene C6H6. So if one hydrogen is being replaced with some other group, oxychrome, it will increase the absorption as well as the wavelength, absorption intensity. That is, for example, if it was without the, but it is increasing its intensity. So example is that, for example, benzene, it absorbs nanometer and it has the epsilon value is equal to 203. That is the absorption. But if one hydrogen of this benzene is replaced with what NH, that is what? That is oxochrome. This is the benzene is the converting into from benzene to aniline. Aniline. Now, if anilines are being observed, so aniline has a lambda max of what? 280 nanometer. Value is equal to absorption of 1430. So again, this is what? Wavelength is changing tremendously. And similarly, its epsilon value is increasing tremendously. This is about 7 times higher. This is 30 nanometer at least. it is absorbing. So it increasing the wavelength, it is also increasing the absorption. Okay. Now, when we say that the absorption as well as the wavelength is changing, absorption intensity as well as the wavelength intensity is increasing, wavelength is increasing, it is so there are the four different types of changes which could be observing. Shifting of the band as a change in the intensity. The changes in the absorption characteristic of the chromophore, both intensity as well as the wavelength, as they can be classified as number one, that is called the bathochromic shift. Bathochromic shift, it is also known as what? Red shift. Yes, it is red shifting toward red light wavelength, which is responsible for the red light. Okay, now max for longer with towards longer wavelength due to the presence of the oxochrome. The oxochrome, if the wavelength is moving towards higher wavelength, we say that this is red shift. It means that N to pi transition for the carbonyl group experience the bathochromic shift. This is the example. When the polarity of the substance decreases, bathochromic shift is there. When there is the addition of what an N to pi transition, the bathochromic shift is taken. So the other way around, that if it is the opposite, that is, if the wavelength is not increasing toward longer wavelength, decreasing, that it will shifting toward lower wavelength, it means that its wavelength is decreasing. So a shift of lambda max to shorter wavelength is known as blue shift. It may rise chromophore is the shifting was taking place. Now it is removal of that. That is the when it is decreasing. Here, when it is increasing, it is going to be a blue shift. That is, the max will be shifting toward lower wavelength. One is the hyperchromic shift. In a hyperchromic shift, that is, this is the increase in intensity. Hyperchromic or the hyperchromic blue shift or red shift, they were due to the shift, due to the change in the wavelength. Now it is increasing. Hyperchromic shift, when the intensity of the intensity of the substance is increasing from the, for example, in the without the bathochromic shift, due to without the additional bathochromic, the intensity is increasing from 0.2 to 0.25, 0.3, 0.4. It means that increase intensity, increase in the absorption is taking place. So that is called as hyperchromic shift. Blood pressure of that component, that patient is increasing. Hyper means higher. It means that if the increase in the absorption taking place, we say that this is the hyperchromic shift due to the introduction of what oxochromic increase the intensity of the absorption band. And if the reverse of it, if the due to the introduction of the observation, if the absorption is decreasing, we say that this is the hypochromic shift. The decrease in the intensity of an absorption band due to the introduction of isochromic is known as hypochromic shift. And this could be, for example, this is the absorption of the epsilon. This is increase. This is zero. This is increasing. There is this is low wavelength. This is high wavelength. When we say low wavelength, it means that the blue color is there. So the blue color is smaller as compared to the red one, which is of higher color, higher wavelength. Okay. Now this is the band, absorption band. If, for example, this lambda, it is shifting towards a longer wavelength, that is towards, this is called as bathochromic shift or red shift. And if it is moving towards the blue color, and if the intensity, if its intensity is increasing from this level to higher one, whatsoever, known as hyperchromic shift. Whereas if its intensity decreasing, it is known as hyper. So these are the shifting. Now, there are the quantity, that is the components of the instrumentation. I am stopping at this topic. We will be continuing this slide after the break. And without break, before we go to break, an announcement for you people. I have distributed. I have given the home assignment for you people, and this will be due date is after 8 days. That is the 4th of the next month. Okay, that is 4th January. You have to submit. You have to write it, and then you will email in the PDF form to the email address given in the assignment number 1. And number 2 is that and the result of this is I am going to announce. So please be attentive and listen your marks. This is these results. The result marks obtained by the people, by the students. Okay. So first one. Okay, number 3. Rabia Ijaz, 37. Javira Yamin, 20. Shama Saifullah, 29. Sumaya Ilyas Chaudhry, 38. Muniba Shafiq, 34. Amir Nawaz, 26. Manahil Ehsan, 32. Amna Bibi, 31. Fatma Batul Beg, 30. Ikra Naseer, 20. Aisha Bibi, 17. Rohit Eric, 31. Samia Ilyas, 12. Suleiman 30. For those Hamid Abbasi 1-4. Taima Batul 9. Sania Said 40. Arij Mustafa 26. Seven. Hafza Nimra Parveen 29. And for those, that is the Saddam Khan 23. Roma Aslam 27. Mansoor Akbar Butt 21. Iram Aftab 30. Pakiza Iram 37. Sayyid Muhammad Osama 37. Shehbaz Wakil 23. Muhammad Rizwan 25. Javeria Shakil 28. Fahim Ahmad Shah 25. Muhammad Bilal Sethi 27. Rehana Aziz 31. Munir Hussain 4 only. 0. So these are the results. So please be careful for next test, which will be on next Monday. So we are going to have a test, and then we will be conducting the remaining class. At this time, we are going to for a break of 10 minutes only. चार्ट पढ़ेंगे वो उसमें इंक्लूडेड होगा पेपर में. And is there any question? Okay, thank you very much. Aisha Bibi is typing. But.